Quantum entanglement is one of the most fascinating and counterintuitive phenomena in modern physics. It is the entanglement of two or more objects at a quantum level, where their properties become so tightly correlated that they seem to act as if they were one and the same. The implications of quantum entanglement challenge our deepest understanding of the universe, from the fundamental laws of physics to our perception of reality. In this video, we will explore the scientific background of quantum entanglement and the philosophical implications that arise from it. At the heart of entanglement lies the phenomenon of superposition, which allows a quantum object to exist in multiple states simultaneously until it is measured. When two or more such objects interact, they can become entangled, meaning that the state of one object is dependent on the state of the other. This correlation can persist even when the objects are separated by large distances, meaning that a measurement of one object can instantaneously affect the state of the other object, seemingly defying the laws of classical physics. One of the earliest and most famous examples of quantum entanglement is the EPR paradox, proposed by Einstein, Podolsky, and Rosen in 1935. The paradox involves a pair of entangled particles, one of which has an angular momentum component pointing up and the other pointing down. If one particle is measured to have an angular momentum pointing up, the other particle must have angular momentum pointing down. However, according to classical physics, this correlation would require some form of instantaneous communication between the particles, violating the limitations imposed by the speed of light. The EPR paradox was eventually resolved by John Bell's famous inequality in 1964, which showed that the predictions of quantum mechanics are incompatible with the assumptions of local realism, a philosophical stance that asserts that physical objects have independently existing properties regardless of measurement. Bell's inequality has since been experimentally tested and confirmed, showing that quantum entanglement is indeed a real phenomenon that cannot be accounted for by classical physics. But the implications of quantum entanglement extend beyond the realm of physics and into the domain of philosophy. One of the most famous thought experiments in this regard is Schrödinger's cat, proposed by the physicist Erwin Schrödinger in 1935. The experiment involves a cat that is enclosed in a box along with a radioactive substance and a Geiger counter. If the substance decays, the Geiger counter triggers a mechanism that kills the cat. According to quantum mechanics, the radioactive substance exists in a superposition of decayed and non-decayed states until it is measured, which would also force the cat's state into a superposition of dead and alive states. This thought experiment highlights the bizarre nature of quantum mechanics, where seemingly absurd scenarios can arise from the principles of superposition and entanglement. It also raises provocative questions about the nature of reality and the role of measurement in shaping it. Does the cat exist in a superposition of states until it is observed, as quantum mechanics would suggest? Or does the act of observation collapse the superposition into a definite state, as classical physics would assume? Another philosophical implication of quantum entanglement concerns the nature of causation. If entangled objects can instantaneously affect each other over large distances, then the idea of causation as a linear chain of events becomes more complicated. As the philosopher of science Nancy Cartwright puts it, quantum mechanics is like having a litter of puppies. Everything is connected to everything else in an intimate way, and you can't touch a puppy without affecting all the others. In conclusion, quantum entanglement challenges our understanding of the universe in profound ways. It forces us to re-examine our assumptions about causality, locality, and measurement, and to confront the limitations of classical physics in describing the world around us. While the philosophical implications of entanglement are still a matter of debate, one thing is clear: the bizarre nature of quantum mechanics continues to push the boundaries of our knowledge and challenge our most fundamental assumptions about the nature of reality.